This video is going to tell you how to integrate over a general region. Now in 15.1, we integrated this double integral f of x, y, dA. This was integrated over a rectangle, so region R. So you see that here. We integrated over a rectangle. We want to be able to integrate over any general region, D. So we want to be able to move on and integrate f of x, y over the general region, D. First, we want to learn a little bit about the types of regions we are going to integrate over. This region here is a very general region, but we have two types of regions that the book does go over, so yeah, please read those, but we'll go over them quickly here. A plane region D is said to be of type 1 if it lies between the graphs of two continuous functions of x. So that is D x, y, given that you got x is between a and b, and you've got a function of x on the lower region, and y is between that and a upper region function of x. So that's g1 and g2 are continuous on a, b. And then here are some examples. So you'll see here in this first example, you've got your g2 is here, and your g1 is here. So you kind of have these flat sides for these type 1s, but you also can have where it just kind of hits a point. Here's a flat side. And here in this one, your g2 and your g1. And then the last type 1 region, you've got a g2 here and a g1 here, and you see how these bounds just hit this region D at just 1 point each here. So that's between A and B. Now for type 2, so type 2 region, we have a function of y on either end of the region here. So we've got, and that's bounded, which we would say bounded by C and D. All right. So here's your function h1, your function h2, and then again you've got this flat line here and line here for C and D. Same goes here. It goes through one line here, and this goes through a point, and you've got your functions. So this is just a little bit of background of the two types of regions. Now looking back at our original region here, again, this is neither type 1 nor type 2. This is a much more general region. And you're able to integrate this as well by you can kind of split the region. But we're going to go to a definition first here. So thus we have the following formula that enables us to evaluate double integral as an iterated integral, right? So we're able to take this double integral and evaluate it using an iterated integral. For type 1 regions, you'll notice that x is going to be bounded by an a and a b value, a constant, b constant values, and you're going to get these two y functions that it's going to be bounded by, right? And so you've got to integrate the f of x, y, dy between g1 to g2 first, here. And then you'll integrate that from a to b dx. Same idea for type 2. So here's for your type 2 region. You're integrating f of x, y, dx between two functions, hy, which is a function of y, and h1, which is a function of y, and h2, which is a function of y. And then that integration continues with c to d, with respect to dy. All right. So we're going to skip those things, and let's do an example. This example I am actually going to take out from example, so this is going to be example 2, and that you can follow along to. It's page 1003. All right, so we need to find the volume of a solid that lies under the parabola, or paraboloid, sorry, paraboloid, x squared plus y squared. So there's our multivariable function, and it's above some region D, bound by y equals 2x and y equals x squared. So fairly straightforward here. Let's draw that. We're going to draw this is just going to be the parabola x squared. I'll draw the other side of this too. That's fine. So y equals x squared is this parabola. And then you've got this line with a slope of 2. So it's going to be something like this. We're going to cross that parabola at some point here. It's going to continue this way as well, right? But we're really looking at the region that's bounded by these two. So let me fill in that region. Okay, great. So we're trying to find the volume above this general region D and below x squared plus y squared. So we're going to get some sort of positive value there for the volume. We need to just make sure that we set up our region D correctly. So the first step is to write that out. Okay, so we're talking about xy. And here are the restrictions on xy. Well, we know the restrictions on y. Obviously, y has to be equal to 2x, and y has to be equal to x squared. Well, we're going to have some sort of intersection here. So we're going to bound our x's, and that's going to be contingent on where the intersection is. So we can just go ahead real quick, and that intersection is obviously going to be when 2x equals x squared. Okay, so let's just make that, I'll actually show you this. Okay. Go ahead and do the zero product rule, right? We're just pulling out of x, right? So we get x minus 2 equals 0 real quick, x equals 0 or 2, right? So we're going to bound it here where x equals 0 and x equals 2. Kind of draw the rectangle if you like. All right, good. So let's display that. So we got 0 between 0 and equal to 2, equal to 0. Comma, we're gonna bound y between x squared and 2x. Great. Now we have our region D. And so we can state that the volume is going to be this double integral over D, x squared plus y squared dA. And we're going to break that into a integrated integral. Zero to 2, that's what we have up here. And sorry about that, 0 to 2, it should look like a 2 there. And x squared to 2x. X squared plus y squared dy dx. And there you go. So you've got it set it up. You can go ahead and do the integrated integral there. And the book on page 1004 will take you through that process. And you'll get 216 over 35. What you want to keep in mind when you do this particular one, because you've got functions here, you want to treat them as constants. So you're just kind of plugging those in, right? Now for this particular example, we can actually, so we treated this here as a type 1. A type 1 region. Right, we treat that as a type 1 region. Why? Because we've got functions, the y is a function. The y is a function of x. Right? And we bound the x's between 0 and 2. We're going to treat it as a type 2 to show you the difference. And again, this is in the book, so quickly, we're just going to solve for x on those two functions. So x will turn up being 1/2 y, and x equals square root of y. So what that means is, again, let's just draw. So we're treating this here as a type 2, so that's going to equal square root of y, and then x is going to equal 1/2 y. We need to make sure that we know the bounds for y as well, right? That's the two parts here. So we've got the bounds for x, we need the bounds for y. So again, to do that, where they intersect, be 1/2 y equals square root of y. So you go ahead and do that algebra, and go ahead, we'll do it real quick here. Right, and again, we've got a quadratic, so we'll just move it over. Pull out a common term, which would be the y. So we got y equals 0, or y equals 4. So here's our bounds for y.